In this lesson, we will examine acids and bases. We will study some of the properties of these substances, some of the key definitions surrounding them, and we'll examine how to perform some basic pH calculations. Now, although you've not studied acids and bases formally to date, you do have experience with acids and bases because there are lots of common acids and bases in our everyday lives. So examples of acids include vinegar, citrus fruits, and bases. A classic base that you've had experience with is soap. You've also had some experience with acids and bases in the lab. Substances like hydrochloric acid and sodium hydroxide are classic acids and bases used in the lab. Now, when scientists classify substances, it's based on their properties. So let's look at some of the properties that define acids and bases. Acids tend to be sour. So if you think to citrus fruits and vinegar, this makes sense. Bases tend to have a bitter taste to them. You may have tried tonic water before, and tonic has quinine, which is a base, and that's what gives tonic water the bitter taste that it has. Acids don't have any noticeable feel to them. However, bases are slippery to the touch, which you've experienced with soaps. Or if you've ever accidentally in the lab had base poured onto your hand, you would notice a slippery feeling on your hands. Acids tend to have specific reactions to metals and to carbonates. And you've experienced both of these before. In our most recent experiment with aluminum and copper, we reviewed the activity series and the fact that some metals will react with acids, hydrochloric acid in our case, to produce hydrogen. You've also had experience with carbonates, perhaps, if you've ever done the baking soda vinegar reaction. Vinegar being an acid and baking soda being a carbonate, when these two substances react, they'll produce carbon dioxide. Bases will have no noticeable reaction with these substances. Now, both acids and bases are electrolytes. As we explore the definitions, you'll see why this makes sense. When they are placed in water, there are ions in solution, which is what allows them to conduct electricity. Acids and bases are also identified using indicators. And you may have worked with litmus before, and litmus turns red in the presence of acids and turns blue in the presence of base, which we can remember with the acid ending in D and red ending in D, and base beginning in blue, as well as the word blue. You've also had some experience with phenolphthalein, and phenolphthalein is an acid-base indicator that is magenta, or a very hot pink in base, yet it is colorless in phenolphthalein. There are many other acid-base indicators that change color depending on the acidity of the solution. Next, what we're going to do is look at the definitions of acids and bases. There are actually three main definitions of acids and bases. And this year we're going to examine two of them. We're going to look at the Arrhenius definition, which is the most basic definition of acids and bases. And then we're going to look at some of the flaws that it has, which will lead to a new definition of Bronsted-Lowry acids and bases. Now, the reason that we have two is because there are certain acids and bases that will fit the definition of the Arrhenius definition very, very well. And then there are a larger number of acids and bases that will fit the Bronsted-Lowry definition very well. And there will be some overlap between the two. There are some that really only fit nicely with the Arrhenius definition. So it's not that the Bronsted-Lowry definition is going to replace the Arrhenius definition. It's just a broader definition that helps us to define a greater number of acids and bases. Now, your experience with acids and bases before in chemistry has been mainly with hydrochloric acid and sodium hydroxide. And you've learned how to name these substances, and you've learned how to recognize that an acid is something that has an H in the formula. Now, what the formal definition of an acid is that it's something that dissociates, produce H plus ions in solution. So when hydrochloric acid, when we break it up into its ions as it goes into solution, it breaks up into H plus and Cl minus. So as we can see, it fits the definition because when it dissociates, it produces this H plus ion. Now it's the H plus ion in solution that gives acids the properties that we discussed in the previous slide. So it's this H that allows metals to react to produce hydrogen. And it's this H that allows us to produce carbon dioxide when we react with carbonates. Bases, by Arrhenius' definition, following the same process, looking at how it dissociates, produce hydroxide ions in solution. You'll recognize a base that fits an Arrhenius definition by having in the formula a metal and a hydroxide. So when this dissociates, it breaks up into the metal ions and the hydroxide ions. If you look back at your solubility rules, the hydroxides were insoluble except with the alkali metals and a couple of the alkaline earth metals. These are the substances, the ones that dissociate in water. These soluble hydroxides are the ones that are Arrhenius bases. Now, by definition, under Arrhenius, when an acid and a base combine, they will produce salt and water. Essentially, what happens when you have an acid and base combining is that you have neutralization. So the acid will lose its acid properties and the base will lose its basic properties, and we will be left with a neutral solution. So let's look at some examples here. These are double displacement reactions. So when you're going to form the products, when you combine an acid and a base, you'll always form water with the H from the acid and the OH from the base, and then your salt will be formed as an ionic compound from the two remaining ions. Now we do need to be mindful of the charges of the substances. So in this case, sodium has a +1 charge and chlorine has a -1 charge. So these will form NaCl. So when hydrochloric acid and sodium hydroxide mix, we have a simple 1-to-1 ratio reaction between the two, forming sodium chloride and water. In the second example, we're not going to have the same neat 1-to-1 ratio. Our salt is going to be formed by combining the sodium ions with the phosphate ions. We still have our H and our OH, which are going to make our water, and our salt is going to be combined by forming an ionic compound between the sodium ions and the phosphate ions. And the phosphate, as you can see from the reverse crossover method, or from knowing your polyatomic ions, has a -3 charge. We're going to do the crossover method here, and we are left with an ionic compound of sodium phosphate, Na3PO4. Our second product is water. Still going to have the formula of H2O. We're not going to worry about the 3 at the moment. It will be balanced when we balance the reaction. To balance this equation, we need 3 sodium hydroxides to balance the sodium, and we will produce 3 waters because we now have 6 hydrogens. So as you can see, we've got 3 H's and 3 OH's making 3 water molecules. Now, although this definition is really useful, it does have its limitations. And there are 2 main limitations. One limitation is quite theoretical, and it lies in the fact that H plus does not really exist in water as a bare proton. Let's take a moment first and address the fact that we're referring to this as a proton. When you have a hydrogen atom, it consists of one proton in the nucleus and one electron. When we form H+, which is the hydrogen ion, by losing this one electron, what we are left with is simply a nucleus consisting of one proton. So H+ is often referred to as a proton. Now, if we were to zoom in and look at a solution of acid, we wouldn't actually see bare protons floating around in the solution. What happens is the water molecules actually hydrate the H+, and so the water will essentially be captured, or will essentially capture the hydrogen ions, and what will form instead are H3O plus ions, which are referred to as hydronium ions. So like I said, this is quite a theoretical definition, and oftentimes chemists will use H plus and H3O plus interchangeably, and what we recognize is that H plus, if we actually were to look in the solution, would exist as H3O plus, but it's still an acceptable form to refer to the ion. So this we formally call a proton, and this one here is called the hydronium ion. A less theoretical limitation to the Arrhenius theory is that some reactions are just simply not explained using this definition. When we look at this reaction here, we've got NH3, which is ammonia, reacting with hydrochloric acid. So we know that this is an acid. And when these two substances combine, they will produce a neutral solution. So what's happening in this reaction is the acid is being neutralized. An acid is neutralized by a base. So from this experiment, we would know that the NH3 must be a base in solution. However, if we look at Arrhenius' definition of a base, Arrhenius stated that bases dissociate to produce hydroxide ions in solution. And this, at first glance, if I ask people in the grade 10 class, or if I ask many of you, you would suspect that this might be an acid, but it actually is a base. So what this means is that the Arrhenius definition does not properly explain the fact that NH3 is a base. And therefore, there's a need for a broader definition that includes such compounds as NH3. And this is why we have the Bronsted-Lowry definition of acids and bases. By Bronsted-Lowry, an acid is a substance that donates protons, so it donates H pluses. And a base is a substance that accepts H pluses. Now what you're going to find is that the acids and bases that fit this definition best are organic molecules. So this formula might look familiar to you. This is acetic acid or vinegar. And this functional group might look familiar to you from our studies in organic chemistry. This is the carboxyl group, and it is the functional group for a carboxylic acid. Carboxylic acids have a proton available for donation. So what's happening here when the acetic acid is placed into water is that the acetic acid will donate a proton to the water. So the acetic acid is essentially losing a proton while the water is gaining a proton. When the water gains a proton, we form H3O+, which you'll recognize as the hydronium ion. And the hydronium ion, as we previously discussed, is really the equivalent of H+. And will be responsible for allowing acetic acid to have the properties of an acid. Now we'll look a little bit further into how to write these reactions later on in the lesson. Bronsted bases are substances that accept protons. So let's look at the base that didn't fit the Arrhenius definition, NH3. So NH3 has the ability to accept a proton from water. NH3 we can draw it's pyramidal, and this is ammonia. Nitrogen always forms 3 bonds and always has a lone pair. And the lone pair is the location for accepting the proton. So this is the position where the compound is able to accept the proton. And when NH3 accepts a proton, it forms the ion NH4+. At the same time, water has lost proton, so we've taken away H+. It's lost a hydrogen atom, and its charge is reduced to OH-. So as we can see, NH3, when it's in water, by Bronsted-Lowry definition, produces hydroxide ions in solution. And it's the hydroxide ions that are responsible for the properties of bases, and therefore ammonia, although it didn't look like it at first glance, actually is a base. Typical Bronsted bases are derivatives of ammonia. And so the amines that we learned about in our organic unit are the ones that will tend to be organic bases. Now there are some substances that are able to either donate or accept a proton, and they're referred to as amphoteric substances. And we've seen already that water in each of these reactions is an amphoteric substance. It has the ability to accept a proton when it reacts with another acid, and it has the ability to donate a proton when it reacts with a base. There are other ions that can behave this way as well. If you look at HSO4-, okay, it has the ability to accept a proton to form H2SO4, which is sulfuric acid, and perhaps a familiar compound to you. Or if it loses a proton, it will form a sulfate ion in solution. Okay? And both of these are potential molecules, and therefore HSO4- has the ability to act as either. And amphoteric substances will just behave depending on what else is in solution. So if there's something that's a stronger acid in the solution, they'll just be forced to be the base, and vice versa. Now these reactions here, under the Bronsted-Lowry definition, are acid-base reactions. And they're ones that involve the donation of a proton from one species to another. So it's no formal finding the salt and the water being produced. Although what you'll learn in your later studies is that these are salts. Now when you look at an acid-base reaction from the Bronsted-Lowry theory, we can identify what are called conjugate acid-base pairs. By definition, a conjugate acid-base pair is a pair of molecules or ions that differ by only one proton. One member of the pair will be the acid because it has the ability to donate a proton, and the other one is a base because it is the proton acceptor in the pair. So if we look at this example here, when we look at what's happening in this reaction, this substance has donated a proton to the water. So this substance is acting as an acid. The water in this case is acting as a base. Now when we try to identify in the products what the conjugate is, we want to find a molecule that differs by one proton. So this substance differs by one proton from this substance. This is acetic acid, and this is the acetate ion. So this is referred to as the acid in the pair because it has a proton to donate. And this is a base in the pair because it would accept a proton to become the acetic acid. The other pair of ions that we have that are conjugate pair are water and the hydronium ion. So in this pair, the H3O plus is the acid because it has one more proton than its counterpart, the water. Let's look at some examples. What we're going to do here is look at how we can write reactions of acids and bases in water, and we're going to identify the conjugate acid-base pairs in the reaction. Now at this stage, you'll be told what the substance is based on the formula, but I challenge you to start to recognize based on the atoms in the formula whether it's an acid or a base. So in this case, you're being told that it's a base, but the fact that it's a base and it's got a nitrogen in it should be noticed. So this is an amine. So when we want to write the reaction of the base and water, we simply write the formula plus the H2O. Now, although it's more advanced than we want to discuss at the moment, you're going to draw this type of arrow, a reversible arrow, when we write these reactions. We're going to be studying for a large portion of the year, next year, equilibrium. And the substances that fit the Bronsted-Lowry definition are ones that we would study by equilibrium. In a nutshell, these reactions are reversible, and we'll look briefly at that in a moment. Now we've identified this substance to be the base, which means that it's going to be a proton acceptor. And so water, which is amphoteric, is going to act as an acid, and it's going to donate a proton. So this is going to act as the base. Now when we accept a proton onto this formula, we are left with CH3, NH3 plus. Okay, and the reason for this, I'll just do this on the side for this one. You want to add a proton. You're adding the hydrogen, so the formula increases by 1 in the number of hydrogens. And the charge is determined by the combined charges. So this had no charge, but this has a positive 1 charge. So the overall charge of the new compound has to be +1. Now at the same time, the water has lost a proton, so we've taken away a proton, leaving us with OH in terms of the atoms, because we've lost an H. And then the charge, I started with no charge, and I subtracted 1. So I'm left with a -1 charge. Now this is a critical skill to be able to identify the formulas of the products with the proper charges. And one way that you can check to see if you're doing your work correctly is by making sure that the charge before and after the reaction is the same. So we started with 2 molecules, so there were no charges, so the charge before the reaction was 0. And when we look at our products, we have 1 species with a positive charge and 1 species with a negative charge. So again, we've maintained our charge of 0. Now our second job here is to identify the conjugate acid-base pairs. And so the pairs, again, are the substances that differ by one proton. So we've got our amine and then our ion here, differ by one proton. In the pair, this is behaving as a base because it has the ability to accept protons. So this one's going to be the opposite, where it's the acid because it has the ability to donate a proton. The water is my acid as the proton donor, and so the hydroxide is the base as the proton acceptor. Now let's just look for a moment at the fact that this is a reversible reaction. So we looked at the proton donation happening in this forward reaction. So the amine accepted a proton as we formed these products. And if we look at this reaction as being reversible, what we can see is that if we go in the reverse direction, this is going to donate a proton to the hydroxide. So it makes sense that it's being referred to as an acid because it has the ability to donate a proton. And it makes sense that this is being referred to as the base because it has the ability to accept the proton. Let's look at a second example. So this time we've got an acid, so we've got C3H7COOH, and you can recognize acids by having this carboxyl group. So this is going to be our acid. It's going to donate a proton to the water, and the water is going to act as the base. The products here, we're going to take away the H+. Okay, so the atoms that I have left are CH3C7COO, and the charge here, I've taken away H+. So I had no charge, and I've taken away one, so I'm left with a negative charge. The water, I've added an H+, so I'm left with H3O+, okay, which is our hydronium ion. If you check the charges, you'll see that they're properly balanced at 0 on both sides. And as expected, an acid will produce hydronium ions in solution. And the conjugates here, this is an acid and this is a base. And the hydronium is an acid. So we'll do one last example here. Okay, this one here is a weak base. And one question that oftentimes students will have when they're first writing these is, does it matter where I put the H+? So does it matter where I attach the hydrogen in the formula? And the reality is, it doesn't actually matter where you put it, as long as your atoms and your charges are consistent and correct. However, if you want to put the H in the proper place, as it would be good practice, what you would always do is put it near the nitrogen in the formula, because that's where the proton is being accepted. So I've just attached it onto the end. And in my previous example, I attached it and joined it with these two H's, because these two are joined to the nitrogen, and then I've attached a third one to the nitrogen. So this is my base, this is my conjugate acid, and they're a pair, and this is my acid and my conjugate base, and they're a pair. So you need to be comfortable writing these reactions and identifying the conjugate acid-base pairs. And another skill that we need to have is to simply identify the conjugates of a substance. So in this case, I'm being asked to identify the conjugate base of the following. And what this means is that I'm being told that this is an acid. If they're asking you for the base, then they're telling you that the substance in front of you is the acid. And by definition, an acid is something that donates a proton. So in order to get the conjugate, what we need to do is take away a proton from the formula. And so in this case, I'm left with CH3COO minus. So again, this one, if I'm being asked for the conjugate base of it, then this is being identified as an acid. And so I need to take a proton away. And if I take away an H plus from this, I'm left with SO4 in terms of my atoms. And my charge, I started with a -1 charge, and I've subtracted 1. So I have a -2 charge. And that's the sulfate ion. We can do the opposite, where we're looking for the conjugate acid, meaning that this is being identified as a base. And a base is something that accepts a proton. So in order to identify the formula of the conjugate, I need to add a proton. So in this case, the atoms, I'll have H3PO4. And the charge is going to be 0 because I had a -1 charge and I added +1. So I have no charge. This one here, when we identify the conjugate, I add a proton and I am left with CH3 and H3 plus. Now at this stage in the video, you may feel like you would like to pause and do some practice associated with these questions. Or you might feel like you want to continue the video and gather all the information before you do practice. But this would be a natural break. What we're going to look at for the second half of the lesson is the pH scale and some calculations that are associated and key definitions associated with the pH scale. Now you have some experience with the pH scale, and things that would be familiar to you is that it's a range. It shows you a range of the pH and gives you a level of acidity of a solution. Some key points on the scale: if the pH is 7, that's considered a neutral solution. If the pH is less than 7, that's considered an acid. And if the pH is greater than 7, then that is considered a base. Now, when you are studying the pH scale, what pH stands for is actually the power of the hydrogen ion. And what we're doing when we monitor the pH scale is we're actually monitoring the concentration of the H3O plus or the H plus in the solution. So when we look at the scale, the solutions that are most acidic or lowest on the pH scale have the highest concentration of H3O plus. And the entire scale monitors H3O plus concentration, and when we are very high on the pH scale, what that means is that we have a really low concentration of H3O plus. Now the square brackets that I'm using are very commonly used by chemists to signify concentration. So when I put square brackets and a substance, that means the concentration of that substance. So this is saying the low concentration of H3O plus. Now because this scale is monitoring the concentration of H3O plus, what we need is a relationship between the pH and the concentration that is derived from the pH scale. The pH scale is actually a logarithmic scale. And many of you have little experience with logs, so what we're going to do is explore the relationship between the concentrations of H3O plus and the pH, and at the same time investigate the idea of what a logarithm is. What we're going to do is we're going to study this range of concentrations of H plus. So if you look at them, all I'm doing is moving the decimal place over 1 And the concentration of H plus is just getting smaller and smaller and smaller as I go down this list. Now what I've done in this second column, and I'll invite you to do, is to rewrite all of these concentrations in the form of 1 times 10 to the negative x. So just basically put these numbers into scientific notation. So for example, this one here, I had to move the decimal place over 7 to the right. So this in scientific notation is 1 times 10 to the negative 7. It would also be really handy for you to have your calculator at this stage. So we're going to look at a couple of examples and learn how to use our calculator in order to solve pH problems. Now, what we're doing here is we are looking at a very large range of concentrations. So I'm looking at 1 mole per liter all the way to 1 times 10 to the negative 14 mole per liter, which is really, 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 really small. Now what we're going to do is we're going to figure out what the log of our concentrations would be. Now, when you have your calculator and you enter log of a number, so if I enter log of 0.1, what I'm asking my calculator to do is to tell me 10 to the what is going to give me that number. So any time you enter log in a number, you're asking your calculator to tell you what 10 needs to be raised to in order to retrieve that number. This is why we put these numbers into scientific notation, because the number 1 is really equivalent to 10 to the 0. So if I want to know the log of 1, I need to know what 10 needs to be raised to in order to give me 1. So 10 needs to be raised to 0. The number 0.1 in scientific notation is 1 times 10 to the negative 1. So in order to retrieve this number, the log of 0.1 is negative 1. The log of 0.01 is negative 2, because 10 to the negative 2 is equal to 0.01, so 10 needs to be raised to the negative 2. You can try it in your calculator. If you take the log, so you press log and then 0.001, you'll see that it responds with a negative 3, because 10 needs to be raised to negative 3, and that's the equivalent number of 0.001. So really, the log of all of these numbers is simply the exponent in my scientific notation. So you might see here a very interesting list of numbers. They're all whole numbers, and they go from 0 to negative 14, which might look like a familiar range of numbers because this is close to, besides the negatives, this is close to what the pH scale gives us. So we're going to work with logarithms, but we're not just going to take the log of the concentration in order to come up with the pH. What we're going to do is we're going to take the negative log of the concentration of H+, and that will give us the pH. So if we take the negatives, all these numbers, what we see is our pH scale. So like I said before, the pH is giving us the power of the hydrogen ion. So it's giving us an indication of the concentration of the hydrogen ions in solution. Now the reason that we study this on a pH scale is, and in a logarithmic scale, is because we can study a really wide range of concentrations on a very simple 14-point scale. And it's much easier for communication, because if you think about communicating with the common public, talking to them about the concentration being 1 times 10 to the negative 10 molar in their local lake, that's not going to have any meaning to them. But when we put these values on a logarithmic scale, people will have a better understanding of what the pH is. Right? They can understand that that means that that is basic and they can understand that 7 is neutral, and above that is basic, and below that is acidic. Now this covers a really wide range of concentrations, and that's really important to note, because although we might think, oh, we've only moved 1 unit on the pH scale, there's actually a large difference between the concentrations of the H plus ions in the solution. Anytime we're 2 units, so if we move 1 unit on the pH scale, that's a change in concentration of 10 times. So the concentration of 1 mole per liter is 10 times more the concentration of 0.1. And what that means is that if we move 2 units, there's a difference that's 100 times in terms of the molarity of the solution. So we need to be mindful of this, because when we're comparing values on the pH scale, especially if we go back to our lake example, a small change in the pH from 5 to 4 might not seem like a big deal. But if you understand that the concentration is actually 10 times greater in that pH solution of 4, then that's going to be a bigger concern. So let's just do a little bit of a practice here on our calculator. Let's take this example, and we want to know what the log of 0.225 is. So I want you to get that value into your calculator and take the negative of that. So you've got the negative log of 0.225. Now what we want to do is reverse that. So I want to undo the log. The opposite of log is 10 to the power of. So if you do 10 to the power of negative of your answer, see what you get. And what you get is 0.225. So taking the log and 10 to the power of are opposite functions of one another. Let's look at that in action in this table. If we take 10 to the negative pH, so we've got our pH values, and we take 10 to the negative, these values, so 10 to the 0, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, what we're getting back is our concentration of H+. So what we've essentially done in this discussion is derived 2 very important formulas. We've derived the formula for calculating the pH, being the negative log of the H+ concentration. And from the pH, if we want to know the H+ concentration, we've looked at the relationship there, which is 10 to the minus pH. So these are 2 very critical formulas. This gives you a visual of when we're studying logarithms, right? The difference between 2 units. Okay? So we talked about this in our previous slide. And there are other logarithm scales when you look at the Richter scale, for example. That's also measured on a logarithmic scale. And again, why we use logarithmic scales is to study a wide range of values on a very simple scale. This diagram here gives you a nice visual of the changing concentration of H+ as we change the pH. So we're going from pH of 0 across to 14. The concentration of H+, written as 10 to the power of the negative pH, so 10 to the 0, 10 to the negative 4. As you can see, as the pH increases, the concentration of the H plus decreases drastically. Now, the thought of there being H plus in the solution no matter what may not be something that you've thought of before. And it's really important to think of solutions as having both H plus and OH minus in the solution. What we have when we have an acid is we have a large concentration of H plus. And when we have a base, we have a small concentration of H plus, which in turn means that we're going to have a large concentration of hydroxide. When we talk about a solution being neutral, oftentimes people will just automatically think that that means that it's not an acid or a base. But what it actually means to be neutral is that the amount of H plus and the amount of OH minus in the solution are balanced. They're the same as one another. So in a solution that's neutral, we still have a concentration of H plus. It's got a pH of 7. So if we want to know the concentration of the H plus, it's 10 to the minus 7. But because it's neutral, that means that it's balanced by the hydroxide in the solution, which is also going to be 10 to the minus 7. Now, although we study the pH scale, it's important for us to also see the relationship with hydroxide and look at a pOH scale. In the lab, we'll always work with pH because the meters that we use will measure the pH, and our indicators are used to measure pH. However, it's important to recognize that there's always hydroxide in the solution, and so we can always study the concentration of hydroxide in the solution in much the same way that we can study the hydrogen ions in solution. So when we look at the hydroxide, we can see the range of concentrations of hydroxide as being exactly the opposite as the range and concentrations of the H plus in the solution. Much like we can calculate the pH of the solution by studying the concentration of the H plus, we'll be able to study the hydroxide concentration by studying the pOH. And essentially, we can put anything into a logarithmic scale. We can take the power of anything. So if we look at the pOH scale, we're simply looking at the power of the hydroxide ion in the solution. And the P of anything is the negative log of that substance. So pOH can be determined by taking the negative log of the concentration of OH minus. And inverting this formula to solve for the hydroxide, using the fact that 10 to the power of is the opposite function of the log, the hydroxide concentration can be determined by taking 10 to the power of the negative pOH. Now this here summarizes when you have the pH, it reminds us whether or not a solution is neutral, acidic, or basic. So when the pH is 7, it's neutral. When it's less than 7, it's acidic. And when it's more than 7, it's basic. We can examine a pOH scale in the same way. So neutral is 7 in the pH scale, as it will be the same in a pOH scale. And what we want to do is look at the relationship. If we think of an acid that has a pH of 6, it has a certain concentration of H plus. The concentration of the hydroxide is going to be lower in that solution. And if we look at these scales, when you have a high concentration of hydroxide, you're going to have a low pOH. So the pOH scale is actually the opposite in that a lower pOH is going to be a basic solution and a higher pOH is going to be an acid solution. So if we look at this, we can see, okay, well, if we've got a pH of 6, that's slightly acidic by 1 pH unit. So on the pOH scale, you're going to have a value of 8, so that it is slightly acidic. If we had a pH of 3 and 4 units away from being neutral towards the acid side, so my pOH in this case is going to have to be 11. And if we look at each of these examples, we can see that the sum in all cases of the pH and the pOH is equal to 14. 7 plus 7, 6 plus 8, 3 plus 11. So these scales can be used hand in hand. And the sum of the pH and the sum with the pOH is always going to be 14. Now from this, we can derive another relationship, which is that the concentration of H3O plus times the concentration of OH minus is always equal to 1 times 10 to the negative 14. Let's look back at this chart in order to help us to see that. When we had a neutral solution, that meant that the concentration of H plus and hydroxide were equal, and they were both equal to 10 times 10 to the negative 7. When we multiply these, 10 times 10 to the negative 7 times 10 times 10 to the negative 7, we are left with 10 to the negative 14. Let's choose another point. If we were at pH of 10, that would mean that the concentration of the H plus in the solution is 10 to the minus 10. The pOH is in turn 4, so the concentration in this case of the hydroxide ions in solution is 10 to the minus 4. And again, when we multiply these, we are left with 10 to the negative 14. Okay. And again, we want to rethink what we mean when we say a neutral acid or base solution. A neutral solution is one where the concentrations of the hydroxide and hydronium are equal. An acid solution is simply one where there's more hydronium than there is hydroxide. And for a basic solution, the hydroxide is in a higher concentration. What this is leaving us with is what I'll refer to as the acid-base chemistry toolbox. We have 6 formulas that we've derived related to pH that are going to help us to do a number of calculations. Let's look at some examples. We want to determine the pH of these solutions. Let's look at some examples. First question asks us to find the pH of some solutions. And what we need to do is determine which formula will be appropriate for finding the pH. And in some cases, it will require 2 steps and using 2 formulas in order to do so. The first question gives us the concentration of the H3O plus. So therefore, we can plug directly into the pH formula, which is that the pH is equal to the negative log of the concentration of the H3O plus. And when we use our calculator to do that, we find that we obtain 1.810. Now, when doing pH calculations, one of the things to note is what's a little bit interesting about significant digits and pH values. What we need to recognize is that the number in front of the decimal place is actually giving us the power of the concentration. So it's giving us the range of 10 to the negative 1 to 10 to the negative 2 in terms of the concentration. Because it's just basically telling us the exponent on the power of 10, it's not really a significant digit. If we think of the number as being in scientific notation, 1.55 times 10 to the negative 2, you know that this value is not associated with the significant digits. And this is connecting us to the fact that we have a pH of 1. It is these digits here that are the significant digits, as you know from reading values in scientific notation. And these ones are the ones that will change the decimal point of the pH value that we have. So when you're recording pH, it's the decimal points that are actually the significant digits. So if we want 3 significant digits, then we need 3 decimal points. For the most part, because most pH meters read to 2 decimal places, you'll find that a lot of times people will simply report their answers to 2 decimal places and not worry too much about the significant digits. This next example, we have the concentration of the OH minus. So we can't find the pH directly, but we can find the pOH first. So the pOH of this solution is 1.64. And to find the pH of the solution, we're going to take 14 and subtract the 1.64, and we're left with 12.35. Now, I really encourage you, because part of doing these problems is the use of your calculator, I do encourage you to do the calculations along with me so that you can make sure you know how to use your calculator. So what you might notice right after my discussion that I've reported this to 2 decimal places, which is pretty standard and within reason for significant digits. This last example, we're given the pOH, so we simply report the pH by subtracting the 10.12 from 14, and we're left with 3.88. And as you know, when you subtract 2 numbers, you follow the decimal place rule. So this is reported to the appropriate number of significant digits. In example 2, we're given the pH of 4.82, and we're asked to find the H+ concentration of a sample of rainwater. When you've got the pH, the concentration of the H3O+, or H+, which as we've discussed as being interchangeable, is calculated as 10 to the power of negative pH. And the answer is 1.5 times 10 to the negative 5. This pH has 2 significant digits, as does my final answer. Now, pH does not have any units. So what we need to do when we're studying acid-base chemistry is remember that although pH doesn't have units, the concentration of the H+ is going to be reported in moles per liter. So we need to be mindful and not forget about our units for our concentration. This last example, we've got the concentration of the hydroxide ion in the solution, and we want to know what the pH of this sample of blood is. Now this is similar to example B, but I just want to show you that there are 2 ways to solve for the pH when you are given the concentration of hydroxide. In the example above, we found the pOH, and then we subtracted from 14 to find the pH. And in this case, we'll use another relationship that we have, which is that the concentration of H+ times the concentration of OH- is always equal to 1 times 10 to the negative 14. So the concentration of H+ in this case is going to be 1 times 10 to the negative 14 divided by the concentration of the hydroxide, which is 2.5 times 10 to the negative 7. And we find the concentration of H+ is 4 times 10 to the negative 8. Now you do need to be careful when you're using your calculator to do this calculation. You want to properly enter the numbers in scientific notation so that you don't have an order of operation problem and you end up with an incorrect answer. Now you can also, by inspection, observe that these values make sense because the concentrations, the exponents, will always add up to -14. Okay, so based on these values, it makes sense I'm adding up to -15, which is in the proper range. If, for example, you got a sum of -23 or +22, then that wouldn't make sense and you would want to go back and make sure that you've done the calculation correctly. Now that I've got the concentration of the H plus in the solution, I can find the pH by taking the negative log of this value, and I find that I've got a pH of 7.40, properly reported to 2 significant digits. Now we're going to have one more discussion about a point of theory in acids and bases, and then we're going to do calculations that are directly associated with strong acids and bases. What we're looking at is what is called the strength of acids and bases. And the strength of an acid or base is actually a property. It's not something that you can change, and it's not to be confused with the concentration of the solution. When we talk about something being strong, we're not referring to the concentration of the solution being a high concentration. In fact, you can have a very weak acid that is of a very high concentration. So these are two very different concepts. The strength of an acid is related to the extent at which the acid or base can ionize in solution. When we look at strong acids, they completely dissociate in water. So what that means is that every molecule of HCl that I put into solution will dissociate and break up into H plus and Cl minus. Okay, so this is a good visual here. If I put 100 molecules of HCl into the solution, I can expect that all 100 of them will dissociate, and I'll be left with 100 H plus ions and 100 chlorine ions in the solution. Now, there are only actually 6 acids that are considered to be strong. We refer to them as the big 6, and it's really important as you proceed in your studies of chemistry that you know and can recognize which acids are considered strong acids. The strength of the acid is related to the strength of the bond. So these bonds are more easily broken than in other cases. Hence, they're able to dissociate quite easily in solution. So we've got HCl, HBr, and HI. And we've got nitric acid, which is HNO3, sulfuric acid, and chloric acid. Now the strong bases also completely dissociate in water. And the strong bases are identified by the soluble hydroxides. So if you look at the periodic table and you look from lithium downwards, and then you look from calcium downwards on the periodic table, what you can see forming is what I refer to as the big little b. So it looks like a lowercase b. And these are soluble hydroxides. So if you look back at your solubility rules, these are the hydroxides that are soluble in water. And being soluble, they will completely dissociate. So for every 100 sodium hydroxides I put into solution, I will dissociate to produce 100 sodium ions and 100 hydroxide ions. The opposite to this is a weak acid, or a weak base, and these will only partially dissociate in water. Weak acids tend to be our organic acids and can be recognized with the carboxyl group. And weak bases tend to be our amines or derivatives of the NH3, which we've previously discussed. These are the ones that we use this funny new arrow, which is our equilibrium arrow, in order to explain. And it's because the reaction doesn't go to completion. All of the reactants that are available don't completely produce products. Only some of them will dissociate. So as a visual here, if I've got this weak acid of HF, if I put 100 molecules of HF into solution, 95 of them might stay intact as HF in the solution, producing only 5 H plus and 5 F minus in solution. So this would be a 5% dissociation. Only 5% of the molecules that I start with actually dissociate to produce products. This is going to affect the pH of the solution relative to a strong acid. And this is something that we spend a lot of time in grade 12 studying. Our focus this year is going to be on strong acids and bases. For now, understanding the difference and being able to recognize that you have a strong acid or a strong base versus a weak acid or base is what we'll need to be able to do. Now, when we want to find the pH of strong acids and bases, we're going to be using the same formulas that we've previously looked at, but we're just going to do some preliminary information in order to identify the concentrations of the hydronium or hydroxide ions in solution. With an acid that completely dissociates, what we'll see is that the concentration of H plus is going to be equal to the concentration of the acid in solution, because as you can see, they dissociate in a 1-to-1 ratio. For bases, if they dissociate in a 1-to-1 ratio, then the hydroxide concentration will be equal to the concentration of the base. But if they don't dissociate in a 1-to-1 ratio, then we'll need to consider the ratio that they've dissociated. Let's do some examples to see how this works. We've got an HBr solution that is 0.148 molar, and we want to know the pH and the hydroxide concentration. So the HBr we recognize from the list as being a strong acid, meaning that it will dissociate completely into H plus and OH minus. Sorry, Br minus. Now the concentration of the HBr in the solution is 0.148, and so what that means is that when this dissociates, the concentration of the H plus will also be 0.148. For every 100 of these, I put 100 of these in the solution, so the concentration of the H plus is equal to the concentration of the acid. From this, I can find the pH of the solution by subbing into the formula. pH is equal to the negative log of the concentration of H plus, and I find that the pH is 0.829. To figure out the concentration of the hydroxide, what I can do is simply plug into my formula, which is 1 times 10 to the negative 14, divided by 0.148. And we'll obtain the concentration of the hydroxide. Number 2, it asks us to find the pH of a sodium hydroxide solution. So this is a base, so I'm going to expect the pH of this solution to be greater than 7. And that's something that you should think about when you encounter a solution so that you can check your answer at the end. This is one of my strong bases, so I know it dissociates completely in solution. And so the concentration of the hydroxide here is 0.0425 because it's in a 1-to-1 ratio with the sodium hydroxide. For every one of these I have in solution, I have one hydroxide ion, so the concentration is the same. I've got the hydroxide concentration this time, so I can't find the pH directly. I can find the pOH first, and then subtract from 14 to find the pH to be 12.63. This next example, I've got calcium hydroxide. And calcium hydroxide is a strong base. It's one of my soluble hydroxides. And when it dissociates, it produces 1 calcium ion and 2 hydroxide ions. Now the concentration of the base is 0.0425. And to figure out the pH, I need to figure out what the concentration of hydroxide is in this solution. Because the calcium hydroxide and the hydroxide are in a 1:2 ratio, what that means is that the concentration of the hydroxide in this case is actually going to be twice that of the calcium hydroxide, which is 0.085. So it's double the concentration. Once I know that information, I can find the pOH, which is 1.70, and the pH, which is 12.93. And let's look at one more problem. What mass of HCl is needed to prepare 350 milliliters of a solution that is of pH 1.1? So in this case, I know the volume of my solution, and I know the goal pH of the solution, and I want to know my mass. So I'm actually going to need to do 3 steps to solve this. I know that my mass will be equal to whatever the moles I need for my solution is, times the molar mass. And I know to find the moles, I'm going to need to multiply the concentration of the solution that I want times the volume. So really, what I need to do is figure out the concentration of the solution first, which I'm going to do by finding the hydronium ion concentration from the pH. So my first step here is to use my formula to find the H+ concentration, which is found by taking 10 to the negative pH. And what I find is that the concentration that I need of the H+ is going to be 0.0794 moles per liter. Because I'm working with a strong acid, working backwards from that concept, I know the concentration of H+ is 0.0794, so that means that the concentration of the HCl is also equal to 0.0794, because they exist in a 1:1 ratio. Now that I know the concentration, I can use my previously discussed formulas in order to find the mass. So I'll find my moles by multiplying the concentration of 0.0794 times the volume, remembering that the volume needs to be in liters, so I'm going to multiply by 0.35. So the moles that I need for this solution is 0.0278, and then the mass I'm going to find by multiplying by the molar mass. This is the moles of the HCl that I need to make the solution, so I'm going to find the molar mass of HCl, which is 36.46. I'm going to multiply by 0.0278, and I find that I need 1 gram. And to be true to my significant digits, I only have 1 significant digit, so I'm only going to report my answer to 1 significant digit. So this includes our lesson in acids and bases.